the claim is, okay, let's write down our claims so far. So our claims so far are, hold on a second here, get rid of that. All right, fermions. Okay, so the claim so far is consider a multi-way graph representing the time evolution of some quantum states. All right, case one, the edges merge, i.e., the path weights add, and well, and this corresponds to bosons, basically. Okay, path weights add, and you get a single quantum state out of these multiple inputs. Case two, the edges don't merge. And the claim is that corresponds to fermions because, okay, the claim is if it is a pure tree, you have to go back to the beginning of the universe to get a merger, i.e., the states will be maximally separated in branch Hill space, i.e., they'll have a phase difference, i.e., they'll be, I don't completely get this, i.e., they will be, they will have opposite phases. And they will never combine. And these states can never get together, i.e., the electrons can never wind up in the same state. Do you agree?
Yep.
That is disgustingly trivial.
Right.
I mean, this is basically the claim that the exclusion principle just says that the essentially world line in quantum space, okay, so essentially the branch time world lines of different fermions do not converge, but they do for bosons. Okay, so the total antisymmetry of the fermion wave function, total antisymmetry with n fermions, this means everything has to be at an opposite corner of branch Hill space. Okay, so the claim is that if we take a random K-ary tree, that then, let's try to get a little bit smaller one. Okay, so we take one of these. Why isn't this a regular tree? Is that because it's a sum of, why isn't this just n levels? I'm confused. Why Okay, there we go. There's a nice binary tree. Okay, so let's say each one of these is a different fermion. I'm actually a little confused by this picture because how do we generate more? It's one thing to have an existing kind of fermion. This is actually generating a bunch of new ones.
Right. So yeah, so the minimal case would be just two paths.
Right, two independent paths. Or n independent paths, right? So then the question there would be, if we have n independent paths and we want to know, so they're just sort of independent in branch Hill space, why do we anti-symmetrize those wave functions? I think that's got to require, a Born rule story. And I don't know whether you've worked again on the Born rule stuff, but I think we do have to work on that. Why exactly is it anti-symmetrizing? As in, what does it mean to be anti-symmetrizing? What it means is that we take the amplitude, so it's the path weight, i.e., we are taking, what does it actually mean? We're taking the various path weights and combining them. What exactly is the formula? So let's say we have a bunch of path weights. So we have an array of path weights, P sub, like this, right? So what we're going to be doing, what is the formula? If we have psi, what's that?
The formula for what?
For the combined fermion.
What, you mean the bra psi ket x
Yes.
tensor ket y plus bra psi ket y tensor ket x equals 0?
Yeah, but that's just one piece of it, right? If you have n particles, there's an anti-symmetrized wave function. The wave function that you get, what's that?
That's for the two particle case. If you want the n particle case, then you just have a tensor product with n vectors in it.
Yeah, but what's the formula? The question is here, we've got these 5 path weights, okay? And the question is, what are we going to do with the, when we're computing the wave function associated with these 5 path weights, what do we actually get? See what I'm saying? So with 2 of them, I understand that with in the case where we just have array p comma 2, I understand that there we can think of that as this is a path weight and the sign of this thing is minus the other one. Great. But in this case, don't we have, what is the actual formula? It's a oh gosh. What do you get? When you compute, right? It's when you take the Born rule thing, right? Instead of in this case, it's P1 minus P2 modulus squared, right? In this case, it's essentially these 2 vectors, and they are combined in an antisymmetric way. It's like the epsilon. Am I totally confused?
I have no idea what we're talking about. So, I mean,
okay.
You have 5 elements here. They form 5. They form an orthonormal basis of some Hilbert space with 5 independent directions.
Yes.
You have anti-symmetry. So I don't understand the problem.
Explain that again.
So, okay, in the 2p case, you just you could just do that on a real line. You can have p of 1 and minus p of 2.
Yes.
Right. In the 5p case, you need more degrees of freedom because you need every pair has to be sort of an inversion of the other. So you can't do.
Let me give this example, which is
you can't do that in a one-dimensional space, right?
Okay, this is what I'm remembering. Okay, this is what I'm remembering. Look. In this case, right, there's a sum over permutations here. Right. This is what I'm remembering. There's a sum over permutations in this case, and in this case, there's the signature of the permutation, the epsilon tensor in front of this.
Yeah, obviously, because it's a tensor product.
But why is it, where do you get the antisymmetry part from?
What?
Am I being totally stupid about this? Where is that?
I just don't understand the question. I still don't understand.
Okay. What I'm asking is, in this case, right? Okay, when you make the measurement.
What measurement?
I'm just thinking about it. I'm trying to remember how the Slater determinant business works and so on. And here. Symmetric wave function. Okay, fine. Exchanging two coordinate variables. Okay, so this is saying the wave function, the combined wave function, is symmetric under the exchange of coordinates here. So in other words, if we're asking what is the amplitude your claim is that in this case here, if we are looking at a thing with five, pieces coming down, you're saying if we exchange two of them, that always corresponds to a factor -1, is your claim.
Right.
Why exactly? I mean, because you're saying that those two things, those two edges, come from opposite sides of Bradshaw space.
Mm-hmm.
I'm just trying to understand more operationally how you get out this determinant here. What is this asking? So this is psi n1. Oh boy. Do you see what my issue is? I mean, I just think there's probably a pretty easy derivation here of why you're saying when these things are all independent, swapping two of them introduces a minus sign. Can you explain that again?
What? Explain what?
Okay, look, we're trying to derive this formula. Okay, we're trying to derive the formula, this, I'm trying to remember exactly what this means. This is the joint wave function of these n separate particles.
Okay, why are we doing this?
Because I'm trying to check what happens in this case when you have n particles. I understand the argument for a pair of particles, why the phases of these two pieces that come from two different paths should be opposite. But I'm trying to understand for n particles. Go ahead.
Why do we care about the Slater determinant formula, which is only a very restricted case?
Well, okay, how do we do it in more generality?
Well, the generality is the tensor product. I mean, am I misremembering? Right? I mean, the only a very small proportion of fermionic wave functions can be written as a single Slater determinant.
I think that's true, but let's walk through. Okay.
So why are we deriving the Slater?
Because it helps me to understand what the hell's going on and to make sure that we are not. Okay, so we've got these five path weights, right? We understand what those are. Now the question is, how do we write? What is the combined wave function is being written like this, right? The combined wave function, go ahead, what?
Sure.
Okay, so that product of states is because that's our best way of writing. I mean, this combined thing I'm just really confused. The combined thing, normally we can write a superposition of states as just state 1 plus state 2, right? And the attributes of state 1 and state 2, both their phase and their magnitude, just get combined, right? But what's being said here is that when...
States.
What's that?
Those aren't attributes of the states.
Well, they're not attributes of the naked state, no. They're attributes of the state as it appears in the multiway system.
Well, neither in the multiway case nor in the quantum mechanics case. So they're attributes of the amplitudes, not attributes of the states.
Fine. Yes, I agree. Okay. So these are the states here. And what we're saying is, okay, how do we derive this formula?
Okay, so
go ahead.
Is that a genuine question?
Yes.
Okay. So at least in the formulation of the tensor products that Xerxes and I have been trying to work out, where you're basically taking concatenation of multi-way rules, right, to take tensor products of branch Hill spaces. Then what the anti-symmetry condition is just saying if we were to concatenate things in a different, in a different order, you would end up with your amplitudes having different phases. Right. That's what we want to prove. Right.
Yes. But what do you mean by concatenating the multi-way systems?
So if I have, in the simple case, if you take two, string multi-way systems that produce a one-dimensional branch Hill graph,
mm-hmm.
and you combine the rules together for those two string systems, you do a join on those rules, okay, then you will generically get a multi-way system with a two-dimensional branch Hill graph. And the claim is...
Okay, this is starting to get somewhere. Okay, let's look. Multi-way system. Okay, so let's take a multi-way system which gives a one-dimensional grid. How do we do that? So we just say A goes to...
Well, in the... Hang on.
Do you mean something like this? That's a one-dimensional. Is that what you mean?
That works, yep.
Okay, all right. So now...
Then if you did... Yeah, B goes to BA or something.
Okay,
sorry, wait, what do you... That's a states graph.
What do you want?
So if you do AA as your initial condition and then ask for the branch Hill graph.
Okay, great. All right, BB here. Okay, now you say I concatenate those two together. And what do I have to do? Do I have to concatenate the initial conditions as well? Probably so. What the hell is that?
So I have some cleaner examples in the bulletin where I talked about tensor products.
Which bulletin where you talked about tensor products?
In the meta-mathematical one where I talked about categorical quantum mechanics and monodal categories. So hang on, so if you take these two multi-way systems with these, I'm just going to copy the code directly from the bulletin with these branch Hill graphs, then you can take this tensor product multi-way system and you can then highlight the individual things. And then if you look at the branch yield graph, that's what you get with this highlighting. Right, so what you're seeing there is a higher dimensional multi-way system that's being spanned by these two lower dimensional multi-way systems.
Okay.
And if you look at the corresponding branch, you can do the corresponding thing with the branch yield graphs and do those highlightings, which I have just pasted in. Okay, so then you see this two-dimensional space that's being spanned by these two one-dimensional spaces that you started from.
Okay, let me understand what's going on here. Okay, so you've got one. You're taking the product of these two multi-way rules. And what do we think happens here? So what is your argument here?
Right. So the key question then is if you try and do this. So okay, so this is now the claimed tensor product state of the two original systems, right?
Yes.
So then the key question is which of the two systems do you consider to be first, and which do you consider to be last? Because in effect, when you impose your coordinatization of branch yield space, that's going to determine kind of which one is which one is at position pi over 2 and which one's at position minus pi over 2. Right?
Fine.
And so then the point is simply, if we swap the order of the elements in the tensor product, obviously it doesn't change the structure of the branch yield graph. That's all perfectly symmetric. But it does change which of the two subsystems is treated as being first, which is treated as being second. And
sure.
So what you're doing is, if you keep consistent coordinatization, is you are, okay, exactly. That's effectively what's happening. So if we're consistently coordinatizing, so that say, one of those, if we're either consistently coordinatizing the states in the tensor product, or if we're consistently coordinatizing the tensor product state itself, either way, you're going to incur a sign change when we do that swap. Right?
Okay.
Because what used to have phase pi over 2 now has phase minus pi over 2, and vice versa.
Sure. Okay, but so let's take the n-dimensional case. I have a feeling that this n-dimensional case is going to wind up being like a statement that the volume is has a totally antisymmetric tensor multiplying the basis thingies, basis vectors.
You may well be right. You may well be right.
And that essentially what's happening is, okay, potential claim. The fermion wave function is very puffy and fills out a volume that is essentially epsilon, antisymmetric tensor Levi-Civita times basis vectors. Whereas the boson wave function is branchially just a point. That's a spelling word. Oh gosh, my dinner. You're going to be up for a while longer, or are you at the end of your wake cycle here?
I would rather go to sleep, but I'm happy to stay up if.
No. Go to sleep. We'll fermions can wait for another day. We're close. Sure. We're close. I'm telling you, we're going to get that. We're going to get that. I want to see that totally antisymmetric tensor come out.
Sure. But I mean, do you agree with the basic structure of this argument? That basic, so with these two multi-way systems, the A goes to AB, A goes to BA. Those are sort of independent, non-convergent multi-way systems.
Yes.
And so the point is that they can be considered to be the evolutions of two different fermions, or two identical fermions in different quantum states.
Maybe. I think we're sliding a little bit in terms of how we're thinking about, what's a single particle evolution versus not. But potentially, yes. I like this better than the pure independent lines, which I'm not really, which I don't think we're going to be able to get very far with.
Right.
And then, but I do like this idea that essentially what's happening is, in the case of a boson, this thing is basically compressing to a point. Whereas in the case of a fermion, if you have n fermions, you're basically being forced to have this volume in branchial space.
Oh yeah, no. That part I completely agree with. Yes, and I suspect you're right about volume formulas and things. I think there's a purely combinatorial way of thinking about it, which has to do with this way of thinking about tensor products.
Right. Okay, so listen, what we're going to find out, the next step, spin statistics. We're getting it. We're close. This is not far away. Spin statistics and spinners. What's going to happen is probably, when projected to make a, quote, spatial slice, the boson case will be two-way, and the fermion case not. And if we can then show how in that projected spatial slice, I mean, I'm telling you, this freaking factor of 2, this 720 degrees. I mean, I assume it works the same way in any number of dimensions, right? Is that true? It doesn't have an even odd dimension weirdness.
I don't believe so.
So I'm telling you, that 720 degrees is going to be the difference between unidirectional and bidirectional edges somehow.
Yeah, no. That part I agree with. Yes.
Yeah. We are close. Then listen, after we get this, he says, with the assumption that we're going to get this, because I think we are going to get this, we got to figure out particles.
We've been putting off too long.
We've been putting particles off too long. And the fact is, we keep on thinking particles are really hard, but they may actually not be.
Right.
I mean, because by the time we've got all these properties of particles, look, spin is the next thing, in my view, roadmap. Next up is spin and spin quantization.
Right.
And I think your ideas about local gauge invariance and how that works are, that then, yeah. Okay, then we just have to get frigging particles. We just have to get what are the topological obstructions, and I bet that's gettable. I mean, the thing that's so crazy about all of this is the extent to which we can do these things in analog toy systems without really going to the full hypergraph story.
Right.
By the way, I really need to go, but I have another comment about the edges of branchial space. I'm going to look at this game tree thing because I have a feeling that in tic-tac-toe, it's going to be more obvious what the edges of branchial space are.
That may well be right. Yeah, for something that's kind of innumerable combinatorially. Yes,
Yes.
yes, that makes a lot of sense.
All right. Anyway, to be continued.
Okay.
All right.
Very quick before you go, do you mind if I quickly show you something? Sorry.
Okay. My dinner is going to be cold, but go on.
But yeah, so I thought you want to see this. So this is how I'm representing in this find higher order logic proof. This is how I'm representing one of these axiom schemas. So you're quantifying over a predicate phi and saying something like phi xy is phi yx. So then from that you can infer specifically that fxy equals fyx. That's the purely equation, kind of a trivial equational thing.
Yep.
And you can see that's being instantiated as the specific axiom.
Yep.
The place what's exciting is if we now have something like this. So this is the induction axiom. We're saying for all phi, if phi of 1 and if for all if for all x, phi of x implies phi of successor of x, then for all y, phi of y is true. F of 1 is true. F of n implies f of successor of f of n. F of n implies f of successor of n. And then from that, can you conclude that f of n is true for all n? And so then that's
wonderful.
And again,
save that. Put that as an example in your find higher order logic proof and save that in the Dropbox.
Okay, sure.
And I need to go have my dinner, and you need to go to sleep, and we will continue tomorrow, and see if we can. I don't know what time I have tomorrow, but anyway, we'll find a time to continue, and see whether we can get. And let's go get fermions. Okay. Talk to you soon.
All right. Bye. Thanks.
Bye.